Hello students, welcome to Eduauraa. Myself Professor Paras Tanna, your physics mentor. Today we are solving MCQs from the chapter Simple Harmonic Motion. The piston and the cylinder have equal cross-sectional area A. When the piston is in equilibrium, the volume of the gas is V0 and its pressure is P0. The piston is slightly displaced from the equilibrium position and released. Assuming that the system is completely isolated from its surrounding, the piston executes a simple harmonic motion with frequency equals to what? Your four options are: option A, 1 upon 2 pi A gamma P0 the whole upon V0 into M. Option B, 1 upon 2 pi V0 into M into P0 the whole upon A square into gamma. Option C, 1 upon 2 pi under root of A square gamma P0 the whole upon M times of V0. And option D, 1 upon 2 pi under root of M times of V0 the whole upon A gamma into P0. Students, first of all we start with the discussion of increase in volume over here. First of all, we are going to assume that piston is displaced by distance x above its equilibrium position. So we can say increase in volume is equals to constant area of cross section A multiplied by increase of length, which we are considering as x. So we say increase in volume, let's say delta V will be equals to A times of x. Now it is given that the system is isolated, means this is like an adiabatic process. There is no exchange of heat between the system and its surrounding. Now in an adiabatic process, students, we say that P is inversely proportional to V raised to gamma, or we can say P multiplied by V raised to gamma is a constant. P into V raised to gamma is a constant, where P denotes pressure, V denotes volume, and gamma denotes adiabatic constant. Students, first of all, we are going to take log on both sides and then we are going to find out the derivative. First step, we are going to find out log of both sides. Students, we get log of P into V raised to gamma is equals to log of constant. Students, log of A into B gives us log A plus log B, isn't it? So we can say here log of P plus of log of V raised to gamma will be equals to log of constant remains as it is. Using property of log again, log P remains as it is plus as it is. Students, log of A raised to M is basically treated as M times of log A. So here we say log of V raised to gamma will be gamma times of log V. This is equals to log of constant. Now we can think about taking derivative. Students, we are taking derivative but in terms of delta. So for log P, the derivative will be delta P by P plus as it is. Gamma is a constant, take it aside. Derivative of log V will give you delta V by V. This is equals to log of constant. Mind you students, log of constant will also be a constant only. And when the constant is alone, its derivative will be 0. So right hand side we get 0. Now we rearrange and we get delta P divided by P is equals to minus of gamma into delta V by V. Now writing this particular expression in terms of pressure P0 and volume V0, we get students delta P divided by P0 is equals to minus of gamma into change in volume delta V, the whole upon volume is V0. Let's rearrange this. So we get delta P change in pressure is equals to minus of gamma multiplied by P0 multiplied by delta V, the whole upon V0. Students, now we have formula for delta P, change in pressure. So now we can think about finding the formula for restoring force. Let's say restoring force is denoted by Fr over here. So restoring force can be taken as delta P multiplied by area of cross section A. We have formula for delta P and that looks like minus of gamma into P naught into delta V, the whole upon V naught, the whole into area A. Students, where there is delta V, we can use A times of X. So we will be getting Fr is equals to minus of gamma into P naught into what about delta V? It is A times of X into A remains as it is, the whole upon V naught. Now students, A into A will give us A square. So we get students, restoring force Fr is equals to minus of gamma into P naught into A will give you A square multiplied by X, the whole upon V naught, students. Now this is of the form Fr, restoring force, which is equals to minus of Kx. So we can say like this, students, piston is executing simple harmonic motion because it obeys the relation F is equals to minus of Kx, which is standard relation for anyone to follow simple harmonic motion. Now students, when we compare this particular two equations, we are going to obtain the formula for force constant K. Simple comparison in these two equations will give us K is equals to gamma multiplied by P naught multiplied by A square, the whole upon V naught. For the piston, students, now we have the formula for K and we also know that piston is going to execute, and in simple harmonic motion, students, we say that the formula for angular frequency, that is omega, is equals to under root of K by M. So students, the formula of K looks like gamma into P naught into area square, the whole upon V naught multiplied by mass will remain as it is in the denominator. So we got the formula of omega. Omega is equals to under root of gamma into P naught into A square, the whole upon V naught times of M. We need the formula for frequency, students. So where there is omega, we are going to use 2 pi n. Further rearranging this equation, we get the formula for frequency n, students. N is equals to 1 upon 2 pi under root of gamma into P naught into area square, the whole upon V naught times of mass M. So my conclusion is the piston executes simple harmonic motion with frequency 1 upon 2 pi under root of gamma P naught into A square, the whole upon V naught times of M. And that's why the correct answer is option C, students, 1 upon 2 pi under root of A square gamma P naught, the whole upon M times of V naught. Moving towards next MCQ. If a spring of stiffness K is cut into two parts, A and B, of length LA is to LB is equals to 2:3, then the stiffness of spring A is given by, your options are option A 5 by 2 times of K, option B 3 by 5 times of K, option C 2 by 5 times of K, and option D K. This MCQ came in IIEEE 2011. First of all, students, we note that in the data it is provided that the ratio of length of part A to part B is 2:3. So we say that LA is to LB will be equals to 2 by 3. Students, the formula for restoring force is equals to minus of Kx. So for a constant force, we can say that K will be inversely proportional to X. Force constant is inversely proportional to X, students. Over here, for this case of spring, we can say that K will be inversely proportional to length, isn't it? Where, students, K is force constant, so K is inversely proportional to L, students. Students, we have to find out the value of Ka in terms of K. So we are going to compare part A of the spring with the entire part of the spring. Students, in case of spring, we can say that the spring constant K will be inversely proportional to the length of the spring, isn't it? So in terms of ratio, we can say Ka divided by K is equals to L divided by LA because K is inversely proportional to length L. So over here, we are comparing part A of the spring with the entire spring, students. So Ka divided by K is equals to L divided by LA. Students, L indicates the entire length of the spring. So we can say L is actually equals to LA plus LB. The whole upon LA as it is. We can split. We get LA divided by LA, which is 1 plus of LB divided by LA. So students, left hand side we are having Ka divided by K. So Ka divided by K is equals to 1 plus the ratio of length of B to length of A is equals to 3 by 2. So totaling up we get 5 by 2. So we get Ka divided by K is equals to 5 by 2. That means Ka can be taken as 5 by 2 times of K. That means the spring constant for section A is equals to 5 by 2 times of K. And that's why the correct answer is option A, 5 by 2 times of K.